day of the IT5437 class on computer vision. So last time we mainly looked at the general landscape of computer vision, starting from the classical vision techniques, early vision, mid-level vision, alignment, multiple view geometry, 3D vision, leading to deep learning based classification, object detection, and generative learning. And then we looked at the very first topic, that was this basics and point operations. We understood how to create an image using Python. It was a very simple function using NumPy. And then we understood color images, and we understood the concepts of resolution and the concept of the dots per inch. So we will once again go through those basics very quickly, and then we will move into this whole array of point operations. These point operations are very important, especially when you want to adjust an image. Now, if you take a photograph and your photograph looks dark, then you want to brighten the photograph. And that operation is a point operation. What that means is the operation only concerns the point or the pixel in question. It does not deal with the neighborhood pixels. Uh, Point operations are also useful, especially in medical image processing. Maybe you have an image, a scan, and you want to emphasize certain regions by brightening them up, certain ranges of intensities. So those things are done using point operations. We will see some of those. And after the point operations, today we will start looking at the so-called spatial operation also. They are the operations are concerned about the neighborhood around each pixel. I hope these things are clear. So as before, you can ask questions at any time. You can use the chat or you can turn on your mic and ask. That's why we do this class together, you and I in the synchronized at the same time. So today also we will have a quiz, a very simple quiz. If you go through the slides, you can answer and get all marks. We have 20 questions, and then we can briefly discuss about those questions also, just to reinforce your understanding about what we do here. Okay, I hope everyone is excited. All right, so let's go through this. So we looked at a grayscale image, and then in this case, we realized, oh, I'm sorry about that. Realized that the primary axis of this image is a vertically downward axis, and then the secondary axis is the horizontally rightward axis. So therefore, when you say pixel 2, 3, we mean 2 in the vertically downward direction and 3 in the horizontally rightward direction. So each of these elements we call a pixel, and those pixels can have values from 0 to 255. The reason is these are 8-bit images. So the data type that we use in Python and in other languages, unsigned 8-bit numbers. So we call them uint8s, not unit, uint8s. So top left corner is 0, 0. This is the very first thing we studied. And this is a grayscale image because there is only one plane. But when you have three planes, BGR, standing for blue, green, and red, you will have a color image. So therefore, a color image can be considered as three grayscale images concatenated together in the third dimension. One thing that we need to know is about the image resolution and dots per inch. DPI means dots per inch. Uh, when you take a camera, you know that it has a CCD or a CMOS sensor. Now, usually, these cameras now have CMOS sensors. Now we can look at an excellent camera. We'll look at an existing camera. We can just search through that. So let's say Nikon cameras. So we can go to some Nikon website. These are excellent cameras. And you can see when you think about, I don't know what this camera is. I don't know whether it's good or bad. I think it's a great camera. So, so mirrorless cameras are the new cameras. You know that DSLR cameras used to be the primary mode of professional cameras. Digital single lens reflex cameras, because there's a mirror and then that mirror opens and so that light comes in. Now, using electronics, you can control that. So therefore, you have mirrorless cameras. So beautiful pictures can be made with these cameras. So this one you can see now for everyone, they will say 29 megapixels. Uh, so if you click that 20.9 megapixels, if you click that, you can see its image quality and so on and so forth. I want to see the technical specifications. So if you look at the yeah, um, technical specifications, power menus, playback monitor, video dash. I think I'm going from down upward, right? Stupid thing to do. Exposure. So many specifications. Lens. You find the file system. Image sensor. So you can see 20.9 million pixels are there. The this has the I think I don't know about this LMS, but you can see 5,568 pixels times 3,712 pixels in that image sensing element CCD. So these are made by Sony. Uh, so most of these sensors are made by Sony. So we can find out which sensor that uses. So those are the image sensors. Mm, you can see they have a hierarchy of image sensors. Uh, if you have time, you can have a look at it. I will just click one of them uh, and see. Uh, so you can see it's 20 megapixels, IM531 sensor. And so they are, if you read more details about that, you would be able to see its number of pixels for the resolution of that. So sensor sizes are given in inches. That means the actual size of that, but it does not matter. That is not what I mean, what we are looking at. The number of pixels they are not giving all at once. So yeah, there you go. So you can see that these different sensors that Sony manufactures, this one is extremely large, right? So megapixels 128. So we were looking at a 20.9 camera. So something like that. So you can see 5,328 times 4,608. So different kinds of parameters are there. We cannot explain all these things at once. But if you are a photographer and you're interested in this, so look at the Sony sensors, Nikon cameras, Sony cameras, and so on. So you can see um, we are concerned about the image resolution. That is a parameter of the sensor that's there inside the camera. But although these kind of dots are produced, the print size, when you want to get a photograph printed, have another parameter that you can control. That is how many dots do you print per inch, DPI. So assume that this area is an inch, okay, slightly larger than an inch. So if I can decide to print 300 dots along the vertical axis, that means 300 pixels. And of course, along the horizontal axis also, you will print 300 pixels. If you think about, let's consider a very simple one. Um, uh, uh, image of 900 times 600. 900 times 600 for convenience. 900 times 600 sensor. That kind of sensors are not there. There's a certain ratio. So this will translate to 3 inches. This will translate to 2 inches if you print this at 300 dpi. I hope you understand what this means. Is there any, why x and y coordinates seem to be swapped? Um, in the slides, yeah, but programmatically, when you do programming, the lower number 1080 is in the vertically downward axis. Yeah, that's an important observation. Yes. Okay. So then we did this exercise yes last time. What we did was we created a NumPy array of 6. Height was 6. You can see this height was 6 and this width was 8. And we created that using the data type NumPy uint8. And then what we did was we selected image pixel 2, 3 and we assigned 255 to that. So that pixel 2, 3 gets full brightness. Then, I mean, this was very simple. Simple to create an image. We created an array of zeros in NumPy, and the size of that array was 6 and 8. But when you do the same thing to produce a color image, so you can see 6 times 8 times 3, because there are 3 planes in the color image. And then when you set the pixel also, you can see you have to give 3 numbers. 3 numbers have to be given. Uh, Now, these 3 numbers correspond to the 3 colors. So since we are creating everything in this case using NumPy, although we have imported OpenCV, we are not doing anything with OpenCV. So therefore, these colors will represent R, G, and B. These are R, G, and B. So remember the color representation used by Matplotlib when you plot it is RGB. Yes. So you can play with this and see. All right. Then displaying using Matplotlib is something that we did. And we can display that using OpenCV also, which also I showed. So this one is the way to open an image. Of course, I'm assuming that this file, whatever I call this file, is in a certain folder. Inside that folder, I'm assuming that this images folder is there. Images folder is there inside that. Inside that images folder, there's a file that is named as jolly.png. With that assumption, I can open and display using Matplotlib. But there is a small thing that we noticed last time. Um, when we uh, open an image using OpenCV, so you can see the image opening is using CV, OpenCV. CV is the OpenCV package. And we are displaying using imshow, which is a Matplotlib function. The color spaces have to be matched. So therefore, we have to use CV convert color. We have to convert from BGR, which is the OpenCV's way of assigning colors, to RGB, which is a Matplotlib's way of displaying images. But you don't have to do that if you use OpenCV itself to show it. But using Colab, you cannot get this working, I think. But on a computer, you should be able to do that. So now I hope this answer is clear. Why do we need to do CB convert color only when displaying using Matplotlib? The reason is we have opened image using OpenCV, which assumes that the image is in the format BGR. And when you are displaying using Matplotlib, which assumes that the image is in RGB, we have to do the color conversion. Yeah, I hope it is clear. If you have any question, as usual, you can always turn on the mic and ask, or you can put in the chat. All right. Okay, then we can display the image properties also. We displayed this last time, I hope. So we have here, you can see opened an image, and then we have displayed that also. So you can memorize these pieces of code to display. And then we are displaying im.shape, which is 2641, 1061 times 3. It's a color image, of course. That's why you have these 3 here. And then the data type, uint8, and then image size, a multiplication of all 3 numbers. is goes there. So if you have any question, please ask me. Then we did this exercise of increasing the brightness of an image. To increase the brightness of an image, I opened the image of beautiful Emma Watson, and I opened that image as a grayscale image. So when you open images using OpenCV, there are parameters that you can give. cv.imread grayscale will open the image in grayscale. Then what I did was I used this cv.add function, and as a first parameter I gave im1, as a second parameter I gave 100. So what it did was it took each pixel here, each of these pixels here, all the pixels, it added 100. You can see the brightness has increased throughout the whole image. Also, one thing that you do notice is the most bright parts of her face have become fully white. Fully white. You cannot go beyond that whiteness. Yeah. Then I asked, what is wrong with this operation? Im equals im1 plus 100. What is wrong with that? Uh, this is the output that we got. So can we have some answers why this has happened? What do you think? Obviously, this operation has produced the correct output, but this operation has led to something wrong. What is the problem? Can you guess? It'll be good if you can type some answers, or you can turn on the mic and answer. Features will be erased. Shows values greater than 255 as black. Other answers? It exists 255 threshold and the program begins from 0 for exceeding values. Any other answers? Yes, I think you are there. So what happens is this now, if you take this uint8 number representation, uint8, you have 8 bits, right? You have 8 bits. So the maximum number this thing can represent is all ones. One, because these are binary, right? One, 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 one. So this corresponds to this amounts to 1. This is 2. These are binary. The third place is for 4. And if you, this is 4, 8, 16, yeah, 32, yeah, 64, 128, right? So if you add these things, all these things, if you add, you will get 255. So the maximum number that uint8 unsigned 8-bit values can hold is 255. So if you add one more to this, what will happen? If you add one more to this, what will happen? All will become 0. If you add 2, the answer will become 1. If you add 3, it will become 2, and so on. So this is like modulo 256. 256. So this is what is happening. Uh, so therefore, you cannot uh, manually add like this to uint8 numbers. So that's why this function is used. This function knows if the result exceeds 255 to put 255 itself. Yeah, you don't put 0 there, 0, a number close to 0 there. This is what has happened there. Okay, good. Then I think this is where I stopped. So we can increase this brightness thing using loops. So I want to show that also. Now image one we have opened as before. Uh, and then I created an image two like the image one. So it will have the exact shape and all these things as image one. Now what I want to do is I want to put values to different locations ij in image two. So how do I do that? I extract the value ij from image one and adds 100 to that. But what is ij? I has to go from the 0th pixel to the pixel here. That one is actually im1 dot shape 0. And this number 02 and this number from 0 to this one is this one. This one, no one more than that. Okay, so that doesn't matter. This is how you write the loop. So I and j. So as we said before, I is the loop that goes in this direction. J is the loop that goes in this direction. So if you're not sure about these loops and so on, I suggested a tutorial which is very fast, the Stanford NumPy Python tutorial. So if you are still not familiar, please go through that. So in Python, you have to nest the loops, you use tab characters like here, one tab here and two tabs there. You can use spaces also. So this is the using the loops, but we don't do it because this is very slow. Uh, in Python and MATLAB and those other interpreted languages, if you're using loops, you should avoid loops. You had to use matrix multiplications as much as possible. In C++, this is okay. All right. Mm. Then we did the color extraction. Mm. We open the image equals CV imread RGB flowers, this image. I will share some of those images with you on the Moodle. Uh, and then what I did was I know that this first number represents the y-axis, right? This y-axis. The second number here represents the j-axis. By putting a colon, I am saying all. Very easy, right? All of I. And here also I'm saying all. And you know that the third one represents the three color planes, right? I will not even say that it is an axis. It represents B first, G, BGR, right? BGR. Those are the colors. So if you put 0 here, 0 means blue, green means 1, red means 2. So you can see indices start from 0 in this case, right? So this, when I say 1, I'm taking all the green component of that and setting that thing to 0. If you put 2 here, I'm taking all the red components and putting 0 there. So then you can see green is gone, red is gone, the image must be blue. So this kind of thing is, I mean, those days when they printed color images, they in offset even there now they are doing that. It's called color separation. So if you are printing like this, but actually you don't print in RGB, you print in CMYK, at least CMYK. So color separation is slightly different from what we see here. Okay, do you want me to do some coding now, or should we do some slides and do the coding? What do you think? Let's do something, right? Let's do a little bit of coding so that though maybe if you did not understand that last time, we can do that. So we have to go to Colab, Google Collaboratory. But actually, I will today ask you to install a Python system on your computers. Mm, Go to collaboratory, and then you can open Colab. So I think I can open the same file that I opened last time. Try this one. Oh, no, no, no. Then I have a problem with the date, right? Yeah, let's open a new one. New notebook. This one is 26th. Okay. All right. Now I need to mount the Google Drive. I hope you remember that. I actually got AI to do that for me. Where is that thing? Oh, yeah. This is the way to mount the Google Drive. That means I should give access to this code to access my Google Drive. Then when I hit run button here, it will ask me certain number of questions to get my permission to access my drive, connect to Google Drive. Fine. Yeah, using this email address. So I hope you have all of you have Google Gmail addresses. Otherwise, you cannot do this. And continue. I didn't even read. Continue. Okay. So okay, now it's mounted. It says mounted at whatever. So content drive. So we have to start working from that location. So you can see this drive is there. And within that, there's a thing called my drive. That's also standard. Within that, I have all these things. I have an image folder for sure there. But that image folder, due to some reason, is not showing here. I don't know that. I don't know why. But that's okay. So let's open but I will show you my images folder using my drive. This is my Google Drive and my drive. And then let's look at the images folder. Images, beautiful images are there. So what we want is to do this color thing. So therefore, I will put that image there. Maybe if you want, I can give you that image, or you can use a image on your own to have these kind of colors. You can see these. This image should have multiple colors, otherwise you won't be able to see the effect of that. So I put that image called RGB flowers. Yeah, that one, RGB flowers. So let's open that image. So for that, I say import CV2 as CV. This is how I get open CV. And then to display, okay, this it's prompting me import numpy as np, and AI prompts import matplotlib.pyplot as plt. Then I will say im equals cv.imread. I want to open that in my contents, content, drive, my drive. There I have images, and then I have RGB flowers dot jpg. If I don't type anything further, it will open it as a color image, but always it's good to assert if im is assert, im is not none, whether the image has been open or image has been open now. So let's do this operation that we understood in the slides. That is the zeroing out the color planes operation. So I'll have to create a copy called in blue because I want to print the blue. And then this operation, let's do that. So in blue is equal to in dot copy. So we get a copy. Then let's okay, it's okay. Let's do the blue one first. Then in blue's one is 0, The second color plane is 0, and in green, okay, it's doing other ones also. Let's let it do that. Let it do that. And then display fig. Yeah, 2 by 2 axis to plot them. In the axis 0, it's showing the original image. Original image. Oh my goodness, it's beautiful, right? It's giving everything that you want. Now, these things I will hit. I mean, gladly hit this thing and get the automatic thing done because there's nothing important in those things. All right, this is what it is. So it will get the RGB images, but will it be correct? Let's do that and see. It's giving red when I say blue. What's the reason? Can someone tell the reason? For blue, it gave me red. For green, it gave me green. Yeah, fine. For red, it gave me blue. What's the reason? Can you guess the reason from previous things that we studied? Yes, excellent. Thank you. Then the cone has said it's VGI to RTV conversion. That is what it is. So thank you. So here I have to say CV.cvt color im cv.color bgr to RGB. This thing, this thing has to be done, unfortunately. So what I will do is I will copy this thing before all the three images that I'm displaying and copy this thing after all the images I'm displaying. Okay, done. Then if I runs that, now, then blue one is blue, green is green, green is, I want to get to the access. Get rid of the access. Beautiful, right? Beautiful, beautiful. It gave me the code. I don't want no access. Yeah, this is nice. I'm happy about it. Yellow flower also has green, right? Yeah, because we don't know that the yellow is composed of some green, green and red, things like that. Okay, this is the code. Any questions about this? I hope everyone is okay. So I'll give you a few minutes for you to do it. I think you'll be happy about it. If you need the image, so I need to give you that image. It's a it's a great collection of images. I spent time in getting those images collected. And as a part of the class, I'm willing to give it to you. Yeah. Okay. Let me try to do that. Put them in the create an image. Yeah, I have my images folder here. I need to put the images folder in the into the images folder. I want to put that RGB flowers image also. Yeah. So now we have Emma's image, Natasha's image, RGB flowers image. Very good. Are we good or can I move forward? Okay. One more minute, please. Okay. Yeah, of course. So in this case, you will notice that 0 means the blue plane. 1 means the green plane. And 2 means the red plane. Yeah. So when you put hash, you get comments in Python, right? Yeah. You have done a Python course though. So while others are doing, in the meantime, if anyone has a question, please ask. We can use this time to answer those questions. Put some images while we are doing that. Let me get rid of these spaces so that you can see the whole code. Some means. Okay, that is okay. Let's move forward. Maybe this code, I can put that in the chat so that if someone missed it, you can use that. Yeah, is the code in the chat. Okay, right. So now let's briefly look at the cameras, but maybe later we will study about the cameras in little more detail. Now, if you take a camera, you know that the light comes from this direction. And a question, after removing the two colors, if we see dark spots, that means contribution from the removed colors are high, or anything else that we can observe from this kind of exercise. Yeah, if you see total black, that means you have fully removed that color. So there has not been a color combination, but those two colors have been the colors corresponding to that area. That's what you saw here. Yeah, that's the observation is correct. So the light goes, and you know that there is this large number of glasses comprising the full lens arrangement. You can see the number 13 is very important. It's called the aperture. The aperture permits certain amount of light to come when you open it and close it. You can use the aperture control of the camera. Actually, if you take a camera, there are three main controls. I think I'm not very good with cameras. The aperture, the shutter speed, and the ISO, sensitivity of the sensor, these things. So aperture you can control, and the shutter speed you can control, and the sensitivity of the sensor you can control. So you can see the reflex and relay mirror, item number 11, you can see it here. That's a mirror. So this is a DSLR camera. It is not a mirrorless camera. So you can see the yellow light that goes from here. It hits the mirror and gets reflected once again from here and there and goes to the eye. So you exactly see the image that the camera main lens sees. And then when you take the picture, when you hit the image taking button, the mirror will be lifted, and then the light will go and strike these things. So item number 5 is what we are after. It's very important. It's called the color and infrared filter. Item number 5. And item number 6 is the sensor that we looked at. These sensors are usually manufactured by Sony. So item number 7 is a shutter. Okay. So now, if you take a DSLR camera, the question is, how does it record color images? Actually, there you can see there is only one sensor, one CCD sensor, 2D array of light sensitive elements. So to record different colors, what the camera does is it has the filter layer. So you can see this one, the filter is so important. What you see here, what you see here is a filter, and that one is, you can see here. So this is the CMOS sensor. So you can see it has elements. So each of these elements is a pixel. Is a pixel. So on top of them, you can see there are filters. These are filters. So this will allow only red light to pass. This will allow only blue light to pass. This will allow only green light to pass. So that means in the CMOS sensor, some elements only receive red light, some elements only receive green light, some elements only receive blue light. So now if you take this element, for example, if you take this element, for example, this one, it does not receive no red light and it does not receive no blue light. It only receives green light. So to compute the green value compute the red value at that location, we had to do so-called interpolation. This is what is shown here. Now, if you take yeah, the green value has to be computed here. I hope this part is clear for you. So the filters are there. Those filters allow red, green, or blue, one of these lights to pass through. So as a result, some pixels are sensitive to some pixels. If a pixel is activated, that means it is producing a voltage, it is red. For some pixels it's green, for some pixels it's blue. Then when we construct, when we display, we know these numbers, and then only we provide color, we using color we display. One question is, you can see green pixels are so many, all others are red and blue. Why do you have twice as many green pixels as red pixels or blue pixels? What's the reason for that? Yes, the reason is, does anyone know why? Many green pixels. Okay. The reason is human eye is more sensitive to green. So it's better to choose green to have as twice as many pixels as red or blue. That's the reason. Okay. So this thing is called the Bayer pattern. This is called the Bayer pattern. And given the Bayer pattern, computing the green value of no non-green pixels, red value of non-red pixels, and blue value of non-blue pixels is called demosaicing. Demosaicing is an important operation that happens inside the camera, inside every camera. But there are expensive rare cameras that are called 3CCD cameras. So you have three image sensors, so three CMOS, but these cameras are rare. I will talk a little bit about color. I do not know too much about color. Um, uh, One thing is, you know that there's a thing called electromagnetic spectrum. Sun and other stars, they produce almost all the radiations from the in the electromagnetic spectrum. So they correspond to very short wavelengths and very long wavelengths. So very long wavelengths ones are usually now in this region. You have infrared. Those are the heat waves that are coming from the sun, infrared. And then beyond the rainbow, you have the ultraviolet, the very purplish light that human eyes do not see. In between, you have the visible range from 400 nanometers to 700 nanometers of wavelength. And we see this as purple and this as red. Yeah. So this is the spectrum that we see. And if you use a prism, you can resolve it and you should be able to see the rainbow corresponding to the white light the prism receives. Yeah. So when you can do additive mixing of that, what that means is if you shine a red light, shine a green light, and shine a blue light, and in equal proportion at the middle, you will see white. So red and green combination is yellow, red and blue combination is purple, and green and blue combination is cyan. So here you can see RGB are the primary colors. Your monitors work with this principle. But if you take the printing industry, you have the subtractive mixing. What that means is now if you do offset printing, usually you have three, I mean, more than four, you have four machines that first prints cyan, magenta, yellow, and uh, black. So this is the CM thing called CMYK. So they are subtractive color spaces. That means when you print something in red on the white paper, what that means is you are, from the light reflected, you are taking off all colors except red. If you print something in yellow, what that means is you are taking off all colors except white in the reflected spectrum. Yeah. This is what printing happens. So maybe we can look at an existing offset machine briefly. So you can see, if you take an offset machine, you can see one, two, three, four things. The paper goes there, but because of the markers at the end, this alignment is extremely good. We can very nicely align. That's why if you want to put red on top of that yellow, very good, they can do that. This is simple one, but you can see there are expensive ones that use more than three inks. So this is 4 inks CMYK, I think. There are other like machine like I mean a better combination of colors to give the nicer sensation, and they can use other metallic colors like green, gold color, silver, and so on. I don't know too much about this. This is the printing industry. Is there anyone who is familiar with the printing industry? We can have a chat with that person. Okay, maybe not. just to summarize, a grayscale digital image is an 8-bit unsigned integer in 0 to 255. We call each integer pixel. Color images have three such arrays of planes, one red, one for green, and one for blue. We can manipulate an image using OpenCV functions of pair of for loops to access each pixel, but which is slower. We don't do that. Yeah. Okay. So now let's briefly look at sampling and reconstruction. Let me take a couple of minutes to see if there are any questions. Any questions? Okay, I'm very happy that you're asking questions and you have joined the class in numbers. Those are good things. So I hope that you can answer the quiz also. These are simple questions. Okay, let's move forward then. No questions. Sampling and reconstruction. So now think about a sine wave. You can see the sine wave here. The sine wave is there. And what if we missed things between the samples? Unsurprising result, information is lost. Surprising result, indistinguishable from lower frequencies. What this means is this. Now think about the black sine curve. Black sine curve. Uh, in this black sine curve, we have taken this sample, this sample, this sample, this sample, this sample, this one, this one, and this one. And given these samples, it is possible. This is a beautiful thing, actually. It is possible for us to draw this light gray sinusoid. Can you see that? So it is a much lower frequency sinusoid than the black one. Yeah, I hope you can see that. Yeah, I hope you can see that. So this is the thing about sampling and reconstruction. So this is called aliasing, signal traveling in disguise as other frequencies. This is aliasing. If you look at these movies, you can look at them later. I will not do it, but you can see wheels rotating in opposite directions and so on. I will not look at it. We can just have a look at it. Can you see the wheel? Wheel is not rotating. Yeah. So this is the thing about aliasing. Um, so this happens when you downsample. You can see crazy patterns appearing. So you can see here also these patterns are appearing here, 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 and so you can see the thing, right? I will skip this slide. So they are also in this one also. You can see the girls' hair is like changing like crazy, right? You can see that because of the aliasing. The people look at them. So okay, so then there's this thing called Nyquist Shannon sampling theorem. Maybe you have heard this. So this is I don't know whether you know this Claude Shannon. Claude Shannon is the father of electronics and father of information theory. So not electronics and digital electronics. So he came up with this so many theorems, including this sampling theorem. A great scientist. When sampling a signal at discrete intervals, the sampling frequency must be at least twice the maximum frequency of the input signal. So you can see this is bad. So um, this input signal has this one is has high frequency, but we have sampled at a lower frequency. This is good. If you sample like this is good. Then the input sinusoid can be reconstructed with that. So how do we get rid of aliasing? Sample more often if you can. That means you have more sample. That means in your image you have more pixels. Your image will be very high resolution. Sometimes it's bad. Otherwise, get rid of all frequencies that are greater than half the new sampling frequency. That is also possible. You get rid of these high frequencies. We lose information, but it's better than aliasing. How to get rid of high frequencies? You apply something called a low pass filter to do that. This is done in before you sample the signal. So you can see if you want to convert that to a CD or something, you do this low pass filtering first. In telephones also, this low pass filtering is done. Okay. All right. With that in mind, we know that if we want to do some operation on the image, sometimes you will have to get rid of the high frequencies of the image. That means you have to blur the image. So we will show you how an image can be blurred later. Okay. Resampling and interpolation is now we are looking at how to make an image large, how to make an image small. Okay. So think about these are the locations of the pixels. How do we reduce the size of an image by a factor of 2? We didn't get complete why we couldn't see the wheel moving in the video completely. Uh, yeah, the because this is not part of this lesson. Uh, um, it's like this. So now this is the reason. Depending on the frequency of the flash. So assume that you're in a dark room and something is rotating. You have torch on off. Torch is on. You turn it on or turn it off. So depending on the time which you on it or put it off, then in this case you can see it appear all the time appears here, right? Not rotating. That's what happened in that. So when you are making a movie, you know that the number of images that you take per second is 24 or something, 24 frames a second. So if the wheel is also rotating in such a manner, those two, I don't know what you call them, to align at 24 frames a second, you will not see it rotating. That's what happens. Okay, but nothing for computer vision, nothing important for computer vision. We just have to know that aliasing thing can happen. So now our question is this. So we have an image. I show the locations of these pixels with this is identical asymptotic. 1, 2, 3, 4, 5, 6, 7. It's a 7 by 7 image. But how do you reduce the size of this image by half? Yeah, you can. How about throwing away every other row and column to create half the image size? Fine, you can do that. But what is the problem that can happen due to this? See, if the image contained frequencies that needed that resolution to represent, and you get rid of them manually, then aliasing can happen like this. So you can see subsampling without, if you don't filter it beforehand. So when you do, crazy things can happen here, right? You can see the crazy things aliasing has happened. But if you do some smoothing before that, then if you subsample, I mean, if it does not look good, but it doesn't contain incorrect information. So this is what you need to do. So drastic example here. This one is horrible, right? This giraffe has appeared in a very horrible manner. See what has happened to the stripes of the giraffe. But here, because after filtering, you do it. It's, I mean, horrible, but it does not contain bad, wrong information. Okay. Now the question is, how do you increase the size of the image by a factor of 2? So you will say that we can some subsample the grid. We can do this, right? We can put additional pixels in between. But how do you calculate the value of those pixels? So I think it is obvious to you. I think you can, if this pixels value is, let's say 100, if this pixels value is 200, this is at the very middle, right? Very middle of this line. It is at the very middle of that line. What a bad choice of color. If you consider the line joining these two pixels, these are the very middle. So therefore, obviously, this value I can get as 100 plus 200 divided by 2, right? You can average it. But this works if you want to increase the size by twice. If you want to do it by 3 times, then there'll be more additional pixels. So you cannot just divide by 2. One you have to multiply by 1 over 3. The other one you have to multiply by 2 over 3 because the distances are different. What should be the value of this one? We need to interpolate. So we have put values to these pixel locations 0, 0, 0, 0, 1, 0, 2, 0, 3, 0. I'm sorry about the uh, convention of these numbers. I should have put it rotated that ing. So this is 0, 1, 1, 0, 2, 1, 1, 2, 1, 3, 1, and so. Okay. Okay, this one is f. If this image we call it f, this f not 0, 1, f 0.5, 0.5, right? I hope everyone agrees with that. Then how do you compute that value? You can, this is f 0.50. So you can say if these values of this 4 pixels are A, B, C, and D. Initially, I took them as 100 and 200, but yeah, these are symbols. So this one you can compute as half A plus B. Very simple. And this one you can compute as half A plus C. This one you can compute as half A plus B plus C plus D plus. Right. So this is what must be done in the demosaicing. But in demosaicing, the algorithm is not as simple as that. They do some very intelligent thing because intelligent things inside cameras because this is a very important operation, the demosaicing operation. But uh, if the uh, image didn't have to be increased by just twice. That means your size of the image is 10 by 10. Now you want to make it 20 by 20. Then you can use the previous formulas, A plus B divided by 2, C plus D divided by 2. But if that uh, interpolation had to be done this distance and that distance are not equal, no? So not at the very middle, right? We want to compute a value not at the very middle. Then you will have to consider the height of A, the value of A, value of B, and not get the middle point, but some point. Then you have to properly do something, some calculation for that to find this value here. And considering C and D, you can find the value there. And considering this and that, you can find the actual value of the pixel in the middle. So this kind of thing is called bilinear interpolation. So here are the equations, but I will not go through the equations. If you have to implement this, you can use these equations and implement. I will just briefly say what the one is. So we want to find the pixel value at x, y. I'm sorry. So you have A, B, C, D as before. So this location is x1, y1. This location x2, y2, x2, y1, x1, y2, x2, y2. So fxy, we call it A, B, C, D, and we have to have this W, these coefficients calculated. These are formulas there. We can derive these formulas, but I will go through that derivation. Very simple derivation, but we don't have to do that. Okay. So bilinear interpolation, it looks like a little bump there. Um, so we, but there are other interpolations. So first one is the nearest neighbor. But nearest neighbor means now you want to calculate the value of the pixel here at this location. Height of this pixel is, we called it A, right? A. Height means value of this pixel is B. So if this is closer to A pixel than the distance to B pixel, we can take A pixel's value itself. This is called nearest neighbor. You take the value of the nearest neighbor. And then the previous linear one, you can sort of draw a straight line and compute the value there. And nearest neighbor in 2D, linear in 2D, it's called bilinear. And then otherwise you can do a cubic polynomial like that. You can draw polynomial. So you need 1, 2, 3, 4 pixel values for that. Just not just 2, but this is very good. And then you draw these cubic curves around and you get it. So bicubic. So you just have to watch it. But if you want to really do the calculations, it will be involving. So if you take the nearest neighbor, the extrema can happen only at a sample location. But if you do cubic interpolation, it can happen in between the pixel locations. Yeah, I hope this is clear. If you have a question, I can ask. Okay, any question? What is the exact definition of aliasing? I don't know. I didn't think about giving a definition. So let's use ChatGPT for that. If you know what you're doing, you can use ChatGPT. Mm. If you try to do it without knowing, then you are in trouble actually. Aliasing is a distortion that occurs when a continuous signal is sampled at a rate insufficient to capture its change, causing different signals to become indistinguishable. Can you see that like, we had high frequency signal, but we sampled it lower, then different signal came. That's a good question. Thank you for that question. Okay. All right. Now what we want to do is to look at another topic called intensity transformations. Okay, another question. So choosing the right interpolation, is there such a thing like by doing it, identify what is the best match for it or matter resource consumption? Yeah, that's a very good question. So when you want to choose an interpolation scheme, uh, you have to know how much computational power you want to spend. Nearest neighbor is horrible, but bilinear is good enough. Bicubic is the best. So Now, if you take photo processing software like GIMP, I don't have Photoshop, of course. I don't have a license for that. I don't have unlicensed software. This GIMP, it's an excellent image manipulation software. GNU image manipulation. Um, you can open an image. So let's say we want to zoom. Scale image. So you can see that you can choose that function, right? Linear, cubic, non-halo, row halo. These things I don't even know, but linear and cubic you know, right? Usually it is cubic. So if you linearly scale it, I think this image is too large. Let's pick a small image. Okay, this is very small image of Taylor Swift. So if you want to mm, scale the image using linear scale, oh, I can say percentage. I'll say 200. Increase it to 200%. Scale, you can see it's scaled. Let me open that again. This one. And image. Scale the image. Let's use the bicubic here. Cubic, and 200%. Twice, that means. What happened? So you can see it's less blockier than the previous one, right? Blocky nature to the linear one is slightly better. I don't know whether I made a mistake, but this is generally the thing. So popular image processing software have this feature of being able to interpolate. If you like, I can give an exercise for you to do image zooming by writing your own code. Okay. So now we want to move to the most important section of these point operations, the intensity transformations, also called point operations. Yes. So I hope you are ready to do this. This is a little bit involving than the previous things. Okay. An intensity transformation uh, transforms the output value of the pixel. In the intensity transformation, the output value of the pixel depends only on the input value of that pixel, not its neighbors. So I'll talk about that in more detail later. But right now, just watch what happens here. Uh, Now, there is a thing called the transformation T. Let's say it's some function, okay? We give it an input image. Let's call the input image fx. And we get an output image gx. So what are the possible values of fx? Intensity values, right? 0 to 255. Because we are considering u into 8. What are the possible values of gx, of a pixel of gx? 0 to 255. Because we are considering u into 8. Okay. So here in this graph, I am representing the possible pixel values of the input image. This is the possible pixel values of the output image. What this line says is, if your input pixel value is 150, the output pixel value also is 150. That's all it says. Similar to all the other pixels. This kind of thing is called, this is called the identity transformation. Nothing happens. Identity. Identity transformation. The input pixel value, 150, goes through the transformation, but nothing happens to it. You get 150 itself. So for all other values, it is the same. So, but if you change this curve to a different one, you can see depending on the input pixel value, the output pixel value will be different. That's the idea of intensity transformations. So now a little piece of code to do that is this. Very simple. Very, very simple. You can see to do this, the code is extremely simple. But it's slightly mind-boggling to understand. But if you understand it once, it's one. So this is the identity transformation that we are considering. Okay, import CV to as CV as usual, the open CV, and import numpy as NP, and we open the image of beautiful Emma Watson as a grayscale image, in read grayscale, you can see. All right, now this is the insanely important function. What does that mean? So I will ask you to look at that for some time. All right, it says NP range 256. What does it generate? It generates an array of length 256 with values 0, 1, 2 up until 255. Let me draw it. So consider that this as that array. This is my T. So it has 0th location, location number 1, and it has last location is 255. So therefore you can see it has 256 locations. All right, because this is the identity function, and we have constructed this using this Python code, 0th location will have 0. Location number 1 will have 1. Location number 150 will have 150. And location number 255 will have 255. Yeah. So you can see input and output are the same in this case, in this array. Input and output, says if this is 150, the output is also 150, defined by the value of this array. So, but now that this array is there, one-dimensional array is there, how do we apply that to every single pixel in the image? Do you have to write two for loops? Yes, you can, but that's a stupid thing to do in a language like Python. You just do this. This is the most important line in this code. F is my image, input image. G is my output image. So I showed you a little picture. This is my T transformation. I have used simple T for that in this case, yeah. And I give it F and get the G out. This can be done by indexing T with F. This operation is indexing T with F. So therefore, you get an array of the size of if F, the input image F, with that transformation. Fortunately, that transformation here is just 1, multiplying by 1. You give an input value, you give the same output value. That's it. So you do this, you get the same, exactly the same image. So which is what we are going to do in Colab. Right, my Colab, did I close it? No. Yes. So, okay. So I want to code. Let's try that identity transformation. Identity transformation code. Import CV2 as CV. Import. Okay, question. Is picking a value and putting in the same location which it was there. So if we drift it a bit, we can move the entire image. Move the entire image. No, there is a misunderstanding there. Change the intensities of the image. Image does not move. Intensities change. Okay, we will do that and see. Actually, we will do that and see. Then you will realize that's a very important question. Import mat numpy as np. Import matplotlib as vlt. So okay, well, let me call it f. F equals cv dot read contains my drive RGB flowers pg. Okay, this is fine, but I want to put the grayscale thing here. cv read grayscale. If I check if the image is not, but I don't want RGB flowers. I want the Emma image. So let's start this and see whether there's an error. There's no error. So I construct the transformation T equals np dot range 256 d type np dot uint8. So this function can be used cv.lut, but I will just do this g equals tf. Now I need to display the two images, so it knows what I want to do. So that one I did not do anything. It's this column array. Actually, v min equals 0, v max equals 1. That thing also will do. Otherwise, there's a change in colors. Okay. So I do not know what happened. See green. Yeah, Vmax is 255. So input and output are same. Now you say you want to slightly change it. So you want to put, other than just NP arrange, you want to do something like this, like T equals T plus 10 or something. That's what you want to do. So it will increase the intensity slightly. I hope you can see. Okay, if you put 100, that wrong thing will happen. Okay. See, increasing the intensity. The pixel location do not change. It increases the intensity, and you know why black came here, right? That you know. So yeah, but this is what I want to do, the identity transformation. So I'll give you some time to code it and experience yourself. Give me a second, I'll be back. Any other questions? So if you want to move the image, spatial operations can do that. We will look at that next time. Moving the image a little. Uh, who needs more time to do this coding part, or is that okay? Identity transformation. Um, so if someone needs more time, please type a message so that I do not start the next thing. Okay, I hope it is okay. So next one I will do the reverse of that. And that means this thing is the identity, no, nothing happens then. But if I change the curve like that, change the curve to like that, what will happen? For every pixel with 250, it will produce 0. If the pixel is 50, it will produce like 205 or something. If the pixel is 0, it will produce 250. You can see produces the negative of the image, right? Negative of the image. Okay. So that's what I'm going to do next. But so simple questions. Explain the line using G user lut FT. So this is also possible using OpenCV. You can do the same operation. This is exactly the same. You use as using this NumPy indexing. It's the one. This can be done using NumPy as this one. So explain this operation though. So T is an array of 256 lengths, and that is being indexed by the pixel values of the image. And it produces an array of exactly the same size as the image with the intensities transformed. What is T here? T is this one, right? T is the identity function here. Okay, so this is the negative of that. So this is the uh, transformation for that. So NP arrange 255, you go up until 0 with step of -1, 255, 254, and so on. So if I draw the arrow, the array again for this case, what a horrible way of drawing, right? I think this is uh, at the 0th location, you will have 255. You don't know anything? And I got that. Hey, draw it again. Okay, let's draw the arrays. It's slightly enough space to draw the numbers. Okay, this is the array. Location number 1, 0. Location number 1, location number 2, some location, last location. So this is the location number 0. This location number 1, 2. Let's call this 150 or something. Just an example in the middle. And then like this location number 255. All right. So let's put in the numbers just to understand what this operation is, NP range operation. At the location C02, you'll have 255. This one is 254. This one is 253. This one is 255 minus 150, 105. 255 minus 200 is 0. This is the what is what it is. So you can see this is the curve, right, of that graph of that. Question, is this a kind of tricky way to manipulate pixels instead of looping? If you write loops, also you can do that. That is correct. And then you can write this operation, for example, this one in the loop. It is possible. But loops are slow, much slow in Python, right? You should not use loops in Python. So this is the way to do that if you are doing it in Python. So uh, yeah, because there are faster implementations for this. That's the thing. So okay. So now let's do this, but I'm going to do that in using my Visual Studio Code. So today, if I have time, I will show you how to get this done in Visual Studio Code. Mm, I have a folder for every course and every year. If you go look at my teaching folder, you can see how old I am from these folders. This is after I came back to University of Moratuwa after my high studies. Starting from 2008, I have folders. Your folder is a 2025 folder. Okay. Uh, okay, I'll just have this notebook. Uh, import CV2 as CV. I'm typing all these things again and again so that you see that if I'm not lazy to type, it's okay to type, right? So please type this and so that you memorize. See, it is always it's annoying. I cannot get the. No, I don't want this. I'm going to use OpenCV to display. That's the thing. So okay, I'm going to hold F, right? F equals CV.imRead. I want to read. I have an images folder. Images. I'm going to load Katrina's image. Yeah, this is what I want to do. All right. So assert if is not none. I don't want messages. Then my T is equal to np dot range. I want to have 255 minus 1 minus 1. Yeah. Then my transformation is G equals TF. That's it. And then I want to display CV dot named window image normal. Yeah. Okay, let's see this first. This one, F original image, open CV. This is running on my computer now. Yeah, this is the one. Okay, so I forgot one command. That's why it's if I don't have that command, the thing crashes. I'll restart it. Okay, run that. This is the original image. So, oh, destroy all windows. See. Hmm. No, it's not running. Kernel is down, dead. Okay, that's okay. All right, now what I want to do is I want to display G also, CV wait key 0, CV dot im show in the same window called image. I will show G. Okay. Okay. Now watch. This is nice. Nice. Not this is not nice. This is something. So please watch. Okay. Is everyone ready? I'm going to run this. Okay. Are we ready? I hope everyone is ready. Okay. I'm going to count 3, 2, 1. Oh, nothing happened. So, okay, I'm lied to you. Let's do it again. Wait key. So wait key means it's waiting for the key. Uh, okay, that's a mistake I did. Okay, let's run this again. Yeah, okay. Three. Are you ready? Three, two, one. Oh, wait key. Mistake. All these things go. I'm so sorry about this. Did not properly type it. And once again, I had to close and open this. That's what happens when you make a mistake with this destroy all windows problem. Open CV display. Wait key properly type this time. I think I'm too excited about this to show you this. Okay, I think this time it will work. Okay, ready? Three, two, one. Oh, can you see this? Oh my goodness. Oh, who wants to see it again? Okay, let me show it again. I think a lot of you want to see it again. This is the original format. A beautiful Katrina. This is who she actually is. Oh, negative of that. Can you see this? Okay. So I hope that was a fun exercise. So for that, I think not I think you need to have Python and everything installed on your computer. Uh, if I have time today, I will show you, but otherwise I will point you to a video. So now let's take a break and we will meet at um, maybe 3, 12:30. Um, 12:30. I hope that is good. You can have something to eat or something and come. Maybe some of you don't have anything to eat. I'm sorry about that if that is the case. Let's post the thing and meet that. Well, that. So we were talking about the intensity transformations that manipulate the value of each pixel individually. The neighborhood pixels do not affect the value of that. So we looked at the identity transformation and the negative transformation, which created that crazy effect. But those are only the simplest. But we can have different transformations by just manipulating that T, the line, the transformation. Maybe you can have a piecewise continuous one like that, comprising 3 line segments. So I have the code in the slides, but I constructed this line as T1, and this line as T2, and this line as T3, and concatenated them here. So this is how I contrasted this transformation T. So you can do that. And here you can see the intensities from 100 to 150. I mean, this is a range of just 50 pixels are shown by a larger range from 50 to 200. So those intensities are vibrantly shown, using a wider range of intensities, right? So that's the purpose of that transformation. So then there's a thing called gamma correction. Hmm. The gamma correction is the curve or the transformation is defined by a simple equation, which is G equals f to the power of gamma. So one thing is we have to convert this. This is the input image. This is the output image. We have to convert f from 0 to 1. Otherwise, this operation is not so meaningful. But we have to convert it back. I will show you how to do that to range intensities from 0 to 255. Now, gamma, if it is from 0 to 1, like a value like this, 0.5. Let's see the effect that happens. Now, these are intensity scaled from 0 to 1. Of course, this 1 corresponds to 255, as you know. I have constrained that by dividing by 255. So you can take small range of dark pixels. Now you'll agree that this range corresponds to dark pixels. These are 0, 1, 2, 3, up until maybe 50 or so. A range of pixels corresponding to dark pixels has been mapped to a wide range of dark pixels. A narrow range of dark pixels have been mapped to a wide range of dark pixels. So this operation is especially important if you see something from a camera inside the room and a window is also visible. I will show you an image like that. So we want to enhance the information inside the room. So gamma equals 0.2 is very important in such a case. But now let's look at the opposite case. That means when the gamma is greater than 1, when gamma is greater than 1, maybe an operation like that. You can see in that case a narrow range of bright pixels. Now these pixels are bright. This range is bright. Has been mapped to a wide range of bright pixels. So white areas are enhanced. That means outside the window, the bright ones are enhanced. But how do you do that? It's very simple. So this is, I'm using a NP array. So the I divide by 255 and raise it to the power. This is the raising to the power of gamma. And once again multiplying by 255 to get it back to 255 for all I in the range 256 from 0 to 255 as type NPU int 8. So this is a comprehension. This is a slightly complicated construction of Python, but we can do that. So I will show this gamma correction. We can do it in Colab or we can do it in your computer. This is the file we are doing. So let's text. Okay. These things let's copy. Wait a minute.
So if you are talking to us, I guess you are mute.
Okay, thank you so much. Thank you so much. Someone came and I forgot to turn it on. So this is what I'm going to implement now. I divided by 255 raised to the power of gamma and multiply by 255 for I in NP arrange 0 to 256. But one thing is you have to convert that to and in uintate. This uintate conversion is extremely important as type uintate. Okay. So let's take another image for that. I want to use it's taking time to upload. Yeah, this one mdr16.tef. Okay. So you can see it became dark, right? Because dark pixels become dark in the if you, gamma is 0.5. So if you put 0.2, 0.0, bright pixels will become brighter. Oh, oh, I forgot to multiply it by 255. So this multiplication I forgot. This one. After raising to the power of gamma, I have to multiply by 255 to get it back to 255. I'll put parentheses anyways because to reduce any confusion there. I'm multiplying the whole thing. So you can see bright pixels are brightened in this case. If you select 2.0, but if you take zero point 0.2, for example, dark pixels will be represented using dark, but the wider range of dark pixels. You can see dark areas have been enhanced. Bright areas have been, you cannot see anything there. So this is the kind of gamma correction code. This is the gamma correction code. But you can see it's very simple, right? This is something called a Python comprehension. You can write an array within thing. So I will put this code in your chat so that you, if you miss anything, you have it. Because getting the video will take a little bit of time. All right, that's good. Mm. So you can see I have shown different values of gamma. Gamma equals 0.21 to 5.51. One doesn't do anything. One doesn't do anything. Gamma equals 2, gamma equals 5, and so on. So you can see different color and brightness ranges get accelerated because of that. Okay, so before moving on, I want to show you that in GIMP also. So these are you can see you have color curves. So with the curves, you can different areas you can emphasize. So now these pixels, let's say, if you want to increase the brightness of these dark pixels, you can increase it like that. Can you see that? You can even do very funny functions like that. You can see like, I mean, this is not gamma correction because this function is so funny so that you can see these areas as well as these areas nicely in this one. But when this is not monotonically increasing, like a little bit crazy, but it's nice, right? Yeah. I hope you can see the value of what you learned now. So all these things have been implemented in image processing software. Mm. So if you open maybe uh, image of a mammogram, I think. Mammogram, I don't know if it's a breast scan or a mammogram. X-ray, it's a digital X-ray. Okay, so now if you apply the curves here, you can, this is the negative. Now you can see the nodule can be nicely seen, right? Very clearly seen. The nodule can be clearly seen. So dark area, so maybe you can do other things also. See, I hope you can see the value of this. Understanding this. So you can see this is a T transformation. That transformation has only 256. It's a 256 array. So manipulating the transformation, you can gain, you can obtain so many effects. Yeah, I hope that these things are clear for you now. Okay, all right. So now let's move to the next one. Let's look at the image histograms. So histogram is a very simple thing. We looked at the histogram when we were in grade 5 or something, like. So centimeter 130 to 135, how many students? 135 to 140, how many students? Like that. That's the histogram. So for the image also, we can create a histogram and then we can look at the distribution of intensities of the image if you know the histogram. So we can represent the intensity distribution over a range of intensities of 0 to 155 using this histogram thing. If H is a histogram of a particular image, H is the histogram. So HRK gives us how many pixels have the value RK, right? So histogram is an array of 256 size. So each location indicate how many pixels are there in that image. So HRK is NRK. NRK is the number of pixels of that color. If you divide it by the full number of pixels, total number of pixels, you can get a probability mass function also. So this histogram that you described by L bits. So L bits means 255 bits. 256, I'm sorry, 256 bits. But we can construct a coarser histogram also. Uh, we can look at that later. Now here's an exercise for you. Build the histogram for this. So this is a 3 by 4 image. There are only 12 pixels as you can see. I have indicated the automatic. Um, I have indicated the pixel values in this. So those are the pixel values 6, 5, and so on. What we want to do is to build a histogram. So it is a 3-bit image, 3 by 4, 12 pixels. So it's a 3-bit image. The maximum value that it can represent, each pixel can represent is 7 because 1, 1, 1, that's equal to 7. So here is the histogram. These are pixels with intensity 0, 1, 2, 3, 4, 4, 5, 6, 7. So are there any pixels with intensity 0? No, nothing, right? With intensity 0, nothing. With intensity 1, nothing. With intensity 2, nothing. Ah, yes, there's this one. That's all. 1. With intensity 3, we have this one. 1, 2, 2. With intensity 4, 1, 2 again. With intensity 5, 1, 2, 3. 3. Of course, if you count the number of pixels in the histogram, you must get 12. 3 times 4, 12. No? Intensity 6, this one is there, this one is there, this one is there, 3 of them again. With intensity 7, 1. This is histogram, very simple, right? This is the histogram of the image. Okay, I hope it is clear to you. Now, we can get the image properties through the histogram. For example, if our histogram is like this, so this is 0, this is 255. What do you think? Is this a dark image or a bright image? So almost all the pixels are in the dark regions, right? So this is a dark image. Now let's take the histogram like this. So this is 255. 0. All the pixels are generally in the bright areas. So therefore, this is a bright image. And if you take a histogram like this, flat, uniform, so this is not bright, this is not dark. All the pixels are equally probably represented. So these kind of images are nice. They are vibrant. So when photographers want to take images, they try to have all intensities represented in the image. So vibrant images. So I will just say V, vibrant image. If you take a histogram like this, something like that. What is that? It's a bimodal histogram. There are two modes in the histogram. Dark pixels and bright pixels and so on, right? Okay. So if the image is dark, the histogram will have many pixel values in the left region. If the image is bright, the histogram will have many pixels in the right region. If the significant number of pixels is in the bright histogram, we'll have two modes, one in the left region and one in the right region. So this is a bimodal histogram. A flat histogram signifies that the image has a uniform distribution of all intensity. Then the contrast is high, the image will look vibrant. Okay. Then there's an operation called histogram equalization. What that means is you took a picture, it's too dark. Now you want to equalize the histogram and you want to make it vibrant. So there is an equation for that. I will not derive that equation. If you like, you can refer to the Gonzalez and Woods book. It has a nice explanation why this is correct. So this is the equation that we want. So this is our transformation T. That transformation you can see is very simple. L is the 256, no? 256. Mn is the total size of the image. So we are assuming in this image, there are m rows and n columns. Then what is Nj? Nj is an intensity number. So you are summing up until intensity K. Okay, this is wrong. This is Rk, T, R, T, K. You are summing up until intensity K. This one, you can see is the cumulative function. Cumulative means you summing up until that, right? Cumulative function. So I will not prove that, but we will do an example. So suppose that a 3-bit image L equals 8 of size 64 by 64, that means M times N is equal to 4096, 64 times 64, has intensity distribution shown in table 4, where the intensity levels are in the range 0 to L minus 1, 0 to 7, carry out histogram equalization. Okay, let's do the histogram equalization for this. So with intensity 0, 790. If I sum this, you get 790 here. So sum up to this one, that means this number and this number must be summed. And you get 790 plus 1023. That means 790 plus 1023. Oh, my calculator is not working. Whatever it is. So here are the numbers. 1830. So you can see after finally, you will get the total number of pixels here. This is the total number of pixels, obviously, when you sum all the pixels, right? Then what you have to do is you have to take this number and multiply it by L minus 1. Here, L is equal to 8. Mn is equal to 4096, and you get a number here, 1.350. And this one, you round it, 3.098 round to 3. So what this means is, um, your array. Now we were talking about the array all the time. That means your transformation T, the zeroth location will tell you to have 1 here. Location number 1 will tell you to have map it to 3. Location number 2 will ask you to map it to 5, and so on. And location number 7 will ask you to map it to 7. This is the histogram equalization transformation. So yeah, I'll give you a minute to look at it. Right. So this is the way of doing that using OpenCV, equalize hist. So when you can see, when you equalize histogram, you get a very nice, very vibrant image. But we will not go into this uh, too more into detail. I have given you the way of doing that using our own code also without using OpenCV, but you should have the accumulated density function for that. But I will not go through this code. You can do it on your own. So if you summarize what we have been doing up to now, basics, we looked at digital images, color images, creating an image in Python, displaying images, increasing brightness and image planes. And we looked at intensity transformations. Those intensity transformations are simply represented by a T, simply by T. And this is the input image, this is the output image. So identity negative intensity windowing we looked at, and gamma correction we looked at, and histograms and histogram equalizations we looked at. I hope that these things are clear for you. Okay. So please do the quiz. This is quite easy. I will do a few questions with you. But we did not do enough material today. The next one I had to start. Okay, I hope this is visible. What is the range of pixel values in an image, 8-bit image? 8-bit means 1, 1, 1, 1, 1, 1, 8 of them. That means 255, so 0 to 255. That's the answer to that. In a color image using BGR format, what does the accessing pixel 2, 3 return? A single intensity value, no. Red, green components, wrong. A tuple of blue, green, and red values. This is the correct answer. Only the red component, the pixel index wrong. What is meant by image resolution? Number of colors in the image wrong. Number of pixels in a row wrong. Number of printed dots per inch wrong. Number of pixels in width and height correct. Number of bytes in an image. This is the correct answer. What does DPI stand for? Dots per inch. C is the correct answer. But don't think that these kind of simple questions will come to the exam. This is just to emphasize understanding. Uh, yeah, there's a question. So when gamma work on global bright or dark, useful features may also be unclear. So contrast limited adaptive histogram equalization helps to save local contrast. I'm not too sure what local contrast limited adaptive histogram equalization means, um, but you can apply histogram equalization locally. That's true. Yeah, gamma correction is an operation that is well defined. The curve is a number to the power of gamma. So therefore, its effects are limited. But you can by manipulating the curve, you can gain lot of effects. What is the NK value in slide 58? It is the number of pixels actually, number of pixels of intensity K. Yeah, no big deal. So, I mean, intensity value 0, 1, 2, up to 255. I mean, that's a very complicated science, right? I think it's not so useful to think about that. But this example that we did is enough. Uh, Again, coming back to the quizzes. Thank you for those questions. What happens when you increase the brightness of grayscale image by adding 100 to each pixel? All pixels values are set to 100. Pixel values are multiplied by 100. Pixel values increase by 100, saturating at 255. Uh, Pixel values are decreased by 100. Pixel values are this is the correct answer. What does the following line of code do? In blue, 0, all pixels 1 equals 0. All pixels 1 equals 0. So that means BGR. Green values are set to 0. Removes the red plane, removes the green plane. That's the correct one. What is aliasing in images? Random noise in images, overexposure in bright images, high frequency signals appearing as low frequencies, lack of contrast in areas, duplicate pixel values. High frequency signals appearing as low frequencies because of the low sampling rate. Okay, so like that you can look at the slides and do these questions. Yeah, so I will not do all. I said I'll do only few. Okay. So let's start with the spatial filtering. Uh, I don't have the the slides uploaded yet because I have to make one more slide, one last slide. I couldn't make it. So I will upload that after I make that last slide. Oh, I showed you the very last slide, right? I'm very sorry about that. Okay, are we ready? Yeah, spatial filtering is like Gaussian blurring images, that kind of thing. So we'll see these are very important to noise filter and so on. So we will see and detect edges. All these things are spatial filtering operations. We will see how these things can be done. We use spatial filtering uh, to Enhance images, example, noise filtering. Anyway, that's also an image processing operation. We can use the same techniques to locate objects in images called template matching. After completing this lesson, you would be able to process images using filters as done in popular image processing software such as GIMP, Photoshop, or GIMP. Intensity transformations affect the brightness, intensity level of an image, what we did before. The resulting value of a pixel after intensity operation is just dependent on the original value of the same pixel. So because it is affected by, as we saw, this t, right? Just affected by this t. So in contrast, the resulting value of a pixel after spatial filtering operation depends on the neighborhood of that pixel. Maybe a 3 by 3 neighborhood, 5 by 5 neighborhood of that pixel. So the space around the pixel in question matters. Hence the name spatial filtering. In linear spatial filtering, we use 2D convolution operation. So we will understand that later. Okay. Are you ready to see with an animation what spatial filtering means? Okay. Now let's try to see how to compute the value of this uh, orange pixel here, this pixel's value using spatial filtering. Okay, that's what we are trying to say. Now we our window or the space around the pixel we consider in this example 3 by, it can be 5 by 5, 7 by 7, and so on. So we call it a window, a kernel, or a filter. Okay, here are the values inside the image. Okay, so now my kernel I am showing at the bottom, and that one is 109, all 109s, and there's a well-defined center, as you can see. So the center we keep at each possible location in the image. Yes. Okay. So each possible location. So here you keep it there. So you underlying values you multiply with the values in this kernel. So here you have 109. That 109 multiplies this 0. Here you have 109, which multiplies this 0. And so on. This 109 will multiply this 180. So 109 times 108 is 20. So therefore, at the corresponding location of the center of the kernel, which is this one, you will get the resulting summation, which is not 0. I think you should get 20. So this is a mistake. I should correct it immediately. Let's correct it immediately. Yeah, you get 20 there. And then you move the kernel to this location. Now you can see 180 is there. And then 90 is there. This one will multiply 180. This number will multiply 90. So 180 times 109 is 20. 90 times 109 is 10. 10 plus 20, you get 30 there. So you can see this is the spatial filtering operation. So in point operations, we design the vector of length 256 t. In spatial filtering, we design this kernel. So this kernel, what you have here right now is all 109s. It's an averaging kernel. It sort of adds all the numbers and divides by the number of pixels inside the kernel, 9. It's an averaging kernel. So again, 40, this mistake is there. Uh, I hope you understand that. Then you get, when you go there, you get 40 again. Then you go to this location, you get 40 again. You go to this location, you get 30. Then you go to the next row, and here you get 40, and so on. You get these numbers. Yeah. I hope that is clear. This number is wrong. As you saw, this number has to be 20. I made a mistake there. Okay. Yeah. So now one thing is you have this row, this row, and this column empty. What's the reason? Because we cannot keep the center of the kernel in any of those locations. Then kernel goes outside the image. Then what can we do? So there are things that you can do. Maybe fill the outside of the image with zeros, or fill the outside of the image as a part of the image, and so on. You can do. So there are things that people have done for that. So practically, the output is smaller than the input. Then you can get output the same as the input if you pad when the kernel is going outside the image, like so. If we pad it with some numbers, these areas of the image, then you can get the same size. Keeping the same size is usually important for every convolutional neural networks. That's all people use that. Your output can even be larger than the input. So, for example, now think about this. To control the size of the output, we need to use padding. What value should we pad the image with? We can do zero padding, as you see here, zero padding, right? That's why you see them in black, right? Padded with zeros. Then your output will have like a dark border outside. You blur it. Wrap around, generally okay. Copy the edge, generally okay. You crop it. Yeah. Reflect around, reflect across the edge. That's also very good. And so on. Yeah. So I hope you understand how to deal with the uh, image boundaries. Any questions about this? Any questions about the spatial filtering operation? Okay, then we can move forward. So now I said that by designing that kernel, you can get different effects. Now this one, this kernel that we looked at 1/9, is just averages, so it blurs out. So we can see these areas have been blurred out of the C-gray image. But if you design the kernel in such a manner that looks like 0 here, plus values in this row, minus values in this row, it will result in computing the gradient in the vertical direction, gradient of the slope in this direction. If you design the kernel this way, positive values there, negative values there, you will compute the gradient in this direction. So you can see these kernels are very powerful. By designing these kernels, you can compute the gradient. So you can blur out an image and do different things with these kernels by designing these kernels. So in the very first lesson, I showed you that people hand design these feature extractors. So kernel design is one of those exercises. But later on, people came up with convolution neural networks. So convolution is running this one of these kernels. It's almost exactly the same, except for some mirroring thing. I will forget about that for the time being. So the weights of the kernel, that means these 1/9s that you see, are automatically discovered by the network. So you don't hand design the kernels, the network automatically comes up with the values for the kernels. That's what convolutional neural networks do. Okay. So this is the code to implement the kernel, implement something like that. So let's write that. Mm, mm. This is the averaging kernel 1/9s. Okay. All right. So I will do that in Colab. What are the images that I have in the Colab? Oh, this one is good, right? But it is called contact lens.tef. You can see sort of. No, no, let's get the C gray image itself. Let's put the C gray image over there so that you can see exactly what you saw in the lecture slides. Yeah, to collect these images, I spend a lot of time, friends. So I need to put that in your Moodle folder also. Let's save. Okay, let's do that. So these codes I will copy now. This also I will copy. Linear filtering. Oh, all this. Okay. Okay. Mm, I want to open the jpg image, JPG, and open that as a grayscale image. That's fine. And I want to get the average if, let's say, AVG average equals. So we have defined the kernel. So in the slides, you can see I have defined the kernel. As ones, 3 by 3 of ones, and I divided it by 9. But this operation here cannot be done in uint 8. Okay, that it knows that. And then we have to, oh, so if you put 5 by 5, I think, not, I think you get, you have divided by 25. This is divided by the kernel. So this operation filter image, we have to give the data type and the kernel. If floating point 32. Let me see whether it is correct. For those things, I usually make mistakes. CV flow CV underscore 32F. CV underscore 32F. Yeah. Okay. F AVG. So we call it a box filter, but I will write averaged. So you can see some blurriness is there in that. If you increase the kernel size, let's say 21 or something, then you can say this. Here also you have to put the kernel size k. Here also put the kernel size k. You have to divide by kernel size squared, right? To make it an average. So then you will see the effect of the blur. You can see it's seriously blurred. But this blurring is not very nice. It has some blockiness, rectangleness in that. So you can please do it by yourselves. But let me erase this and do what we did in the slides. Yes. If you have any questions, please do not hesitate to ask. Ask at any time. I'll be very happy if you ask questions. Actually, I do not like online classes. Maybe you have heard in the department, all our classes are in person. People have to come uh, because then you can have an interaction, right? If some of you are willing to come, I can go into a room where there's a TV and we can do the class there. It'll be much more fun. So some people can do it over Zoom. Others can come to class. If someone is willing, please let me know. I'll be very happy. You can do that. While you're looking at it, I'll create a WhatsApp group and send you a link so that you can join that. I can quickly pass messages to you. The group is not is correct. I'll send the link over chat. Please join that so that we can, if I have message, I can quickly send. I hope some of you can join quickly. Thank you. Thank you so much. Okay, now this is the secret thing. If you want to do the Sobel filtering, so we can copy that. We have to design the kernel. So rather than saying NP array here, I had to say, I thought, oh my goodness, it knows. We have to do the float computations, the floating point. Sobel horizontal. So, but this one has a problem because it does not show the negative values because this Sobel filtering can have negative values because it has negative values. So we have to do some normalization. Uh, yeah, I will write the code for that normalization. It's very important. We can do it like this. Now you can see what you want is there. Otherwise, you can use CV normalize. It's always giving that. That's okay. So you can see you subtract the minimum value because it's a negative value you get, and then you divide by the range and then multiply by 255. So this is the horizontal color. Then we can have the other one, so will be also. So I will print these things later. Print horizontal gradients, vertical gradients. This is number 2. Yeah, figure size is not enough. Not enough. So you can see vertical gradients, the horizontal lines have been emphasized. In the horizontal gradients, vertical lines have been emphasized. This is the original image. So you can see the code for that. You can ask questions if you have. So the kernel will copy here. Okay. I hope this is clear for you. If you have any question, please do not hesitate to ask. Okay, so we have reached the time. So we did some spatial filtering today. So we will continue with the spatial filtering next time and understand how these gradients and Gaussian filtering, blurring, all these kernels can give rise to them, how to design those kernels, the meaning of this Sobel kernel. So you can spend some time to understand these Sobel H and Sobel V. So you can see if you type Sobel H and print it, what we designed. So this is an array like -101, -202, -101, right? So the vertical one, you can see these are positive, this is 0, these are negative. So it computes the direction in the vertical direction. This computes the gradient in the horizontal direction. Sorry, I'm spending too much going over time. So if I have any questions, I will answer. You can stay and ask any question. Otherwise, we are done with the official class. Thank you very much. You can please log off. You can have you can stay and ask questions. I will stay in the class for some time. Otherwise, you can log off. Thank you very much. I hope that you gained something today also. Thank you very much, everyone.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
So when was there still situation we need to create kernels by hand in specific areas? Yes, for some things we have to create kernels by hand because for if you want to compute the gradients, uh, these are operations that we need to do extremely fast. So hand designed kernels are the best ones for that. But if you want to detect specific thing, detect a dog, cat, and so on, these kernels will be automatically designed within the convolutional neural network. So we will see those things. That's a very good question. But if we very well know the operation, we can design the kernel for that. But if you know the end operation, detect an object or something, it's a faraway objective, then we don't know how to design the kernel. So you use so many kernels in a convolutional neural network, you miss not just one, two, or three, you use hundreds of kernels. Yeah, thank you very much. That's an important question. Thank you. So we will stop the recording.